last year, I talked about this class of matroids called laminar matroids, and they're closely connected to these guys called nested matroids that have been discussed and defined in lots of places. Our story starts off long before I was born, when James was working on a paper with John Rowe and his student Kevin. And they, among other things, decided that a matroid was nested if and only if its cyclic flats formed a chain under inclusion. We like to use the word Hamiltonian flat to denote a flat that has a spanning circuit. And doing just a tiny bit of finagling, we can say that a matroid is nested if and only if its Hamiltonian flats form a chain under inclusion. And then we have to define what a laminar matroid is, and in order to do that, we need to talk about what a laminar family is. And a laminar family is a collection of sets such that we're not allowed to have any proper Venn diagrams. So if two circles intersect, then one has to be completely contained inside the other. Formally, it looks like that. And then to define a laminar matroid, we need a finite set, a laminar family on that finite set, and then a capacity function. And we say that a set is independent if for every A inside our laminar family, the intersection with A has size less than or equal to the capacity of A. Is that all right? Last time we talked about how we could remove superfluous information, and if we do that, then essentially we get that our laminar family is just the collection of Hamiltonian flats, and this lets us know that a matroid is laminar if and only if, for each element E that's not a loop, the set of Hamiltonian flats containing E form a chain under inclusion. So now we have these two similar definitions of nested matroids and laminar matroids, and we can generalize that to what we call K-Closure-Laminar Matroids and say that if for every set X with the rank of X being K, the Hamiltonian flats of M containing X form a chain under inclusion. So some things that we know about these guys is that first off, the set of K+1 closure-laminar matroids contains the set of K closure-laminar matroids. And also if we have a matroid that is rank at most K+1, then the only way that we have two circuits that intersect in size K will either both of the circuits have to have rank K, in which case they have the same closure, or one of the circuits has to have rank K+1, and then we have a Hamiltonian, and then we have a spanning circuit. So anytime we have a matroid with rank at most K+1, that matroid is K-closure-laminar. And since they're non-representable rank 3 matroids, that tells us that for K is bigger than or equal to 2, they're non-representable K-closure-laminar matroids. For K equals 0 or 1, or for nested matroids and laminar matroids, we already knew that the classes were minor closed. It turns out that for K equals 2 and K equals 3, those classes are also minor closed. But for any K bigger than or equal to 4, our class is not minor closed. And we actually use Sage a bit to discover a counterexample because we knew we wanted a matroid that did some things, and so we were able to ask Sage back and forth if it was actually a matroid. So to back up to, we know that a matroid is nested if all of its Hamiltonian flats form a chain under inclusion. Doing a marginal amount of circuit elimination, we can just say that if the two circuits intersect, or if the two circuits intersection, so we always have that one circuit is contained in the closure of the other. And if we have a laminar matroid, that using circuit elimination, we can say that if two circuits intersect non-trivially, then one of the circuits has to be contained in the closure of the other. So we can define K-laminar matroids. If the circuits intersect in size at K or more, then one circuit has to be contained inside the closure of the other. And we get that for all K closure-laminar matroids, I said that backwards. So K+1 laminar matroids contains the class of K-laminar matroids. And K-Laminar Matroids also strictly contain the class of K-Closure-Laminar Matroids for K bigger than or equal to 2. And we always get that K-Laminar Matroids are minor closed. So for nested matroids, if we want an excluded minor, we take 2 just graphic cycles of size R, and then we take the resulting matroid and truncate it down to rank R. And that gives us our collection of excluded minors for nested matroids. For laminar matroids, we do almost the same thing, but instead of taking 2 cycles that don't intersect, we take 2 cycles that intersect in exactly 1 element, and we truncate the resulting matroid down to rank R. For 2-closure laminar, there's 2 ways to make 2 cycles intersect in 2 elements or in 2 closures. The first way is to just have 2 elements that the cycles intersect in and have no chords of either cycle. And secondly, we can have this triangle where we have this red circuit, blue circuit, and they each have a chord of the other. In both cases, our circuits still have size R. If we truncate that down to rank R, we get excluded minors, and that's all of them except for 1. If we relax the circuit hyperplane of K to 3, we get the last excluded minor for 2-closure laminar matroids. And then for K-laminar, we do almost the same thing, but instead of having 1 edge here, we have 2 edges because we want the cycles themselves to intersect in 2 elements instead of the closures to intersect in rank 2. And then if we truncate those guys down to rank R and add in the relaxation of a circuit hyperplane of K23, those are all the excluded minors for 2-closure laminar. Thank you.
Are there any questions?
Do you know a counterexample to show that K-laminar is not closed under minors for certain K?
Yeah, so I found this by playing with just deciding what I wanted my circuit closures to be, then asking Sage whether or not I had actually decided on a matroid. James was very unhappy with this because it was just some random thing out of nowhere. So he wanted a way to construct the matroid using operations that we had. And the way to do that is to start with this graph where we have this B guys. So we have a cycle over here and a cycle over here. And then we have this element here that we're going to get rid of. So we want to take the matroid, and we want to do a 2-sum, so we can add these 3 elements here, and that'll make all of the A sub I as a circuit and all of the B sub I as a circuit. And that essentially what it does is it pushes all of these guys. They're not in the closure of the B circuit, but they're in the closure of the B circuit unioned with E, because we truncated down to rank K plus 2, which is the rank of the B guys and E. So that puts all of these A guys in the closure of the B guys. And it puts this B1 in the closure of the A guys. So that gives us that these 2 guys are Hamiltonian flats of M contract E, and they intersect in just too many elements.